Thanks, Kai, for the nice introduction, and thank you for coming here at 9 o'clock in the morning on Monday. I appreciate that. So today I'm going to talk to you about, the title is a bit lengthy, so the main focus will be electronic health records, and I'm going to touch two things. The first thing is how can we do temporal abstractions of electronic health records and build predictive models for a particular problem, for adverse drug event detection. And the second thing I'm going to talk about is interpretability of time series. It's slightly relevant to electronic health records because one form of data there is electrocardiograms. I can tell you, I will spend like 1 minute telling you a little bit about our department. So as Kai said, I come from Stockholm University Department of Computer and System Sciences. This is our very nice building here like newly built, like 4 years old now. And we are quite big, so we have about 5,200 students, bachelors and masters, and we are 178 staff members. 1/3 is teachers, like professors, associate professors, and lecturers. And these are the current trends or the current topics that we're looking at: sequential temporal data mining, interpretability, explainability, random forest and ensembles, and then machine learning for healthcare applications. That's one of our hot topics currently. And of course, we do have a nice group working on clinical text mining and natural language processing. And this is a sample of 3 projects. Of course, we're not working only on health records. We have 2 big projects on electronic health records, one by the Swedish Research Council and one by Stockholm County. And this is a project funded by Huawei, well, the good part of Huawei, not the very evil part, on network traffic prediction on 5G networks. And this is quite a cool project, actually, but I can talk to you about it another time. So today, this is the outline, and this is mainly, I'm going to be covering or summarizing 2 papers, and then you can, of course, read them on your own. So the first one will be on, it appeared just recently, that's on the journal BMC Medical Informatics and Decision Making, and that's open source, so our department liked that a lot. And the second one is appeared at ICDM this year, or in 2018. Okay, so let's start with the first part. So what is an electronic health record? So there are many different definitions, and this is an evolving concept, but for us, we can see it as a longitudinal collection of electronic health information, including patients and populations. Okay. And it's a quite rich data set, and it contains diagnosis in the form of ICD-10 codes. It contains drug prescriptions or that the doctors prescribe to patients or patients pick up from the pharmacy. These appear in the form of ATC codes, as they're called. And then it contains also clinical tests. Tests are more also both procedures. So if you go to do an echocardiogram, that will be a procedure. Or if a blood test is prescribed for you, then all the blood measurements will be available. And then we have more complex structures, for example, clinical notes. So if the doctors after every visit, they would write some comments, and we have several of those. In Swedish, this was also a very good reason for me to become fluent as soon as possible. Then we can also have medical images, MRIs, electrocardiograms, and in principle, we can get access to pretty much everything. At the moment, we have access to most of those, not so many MRIs and medical images, but everything up to clinical notes and electrocardiograms. What is more interesting is that it's in Sweden, there are mainly 5 players that are working on that are covering the electronic health records of the medical centers and hospitals. So the 5 top players are Siemens, the 3 top are Siemens, Cambio, and Com Group from Germany. We are actually looking at the Take Care data set or system that Karolinska University Hospital is using. And mainly, as you can see, the main problem is that those systems are not interconnected. So each county in Sweden has its own system, and typically they have their own configuration. And as a simple example, so the Cosmic EHR system, it's adopted in 8 different counties, and each one of them has its own configuration, making it 8 different systems. Okay. So integrating those systems together, it's a big project in Sweden, and it will take long to be accomplished. But this is excellent for us because it gives us heterogeneous data sources to work on, and good source for funding as well. So currently we have rather large corpus at Stockholm University that keeps growing. We call it the Health Bank. And it mainly contains information about now, well, I say over 1.4 million patients. It should be about 1.5 or 1.6 at the moment. It spans from 2007 to 2014. And mainly it is offered to us from the Karolinska University Hospital, pretty much de-identified, meaning the personal number of each patient is removed, and any private information in the text when the doctors write about the patient is also removed. And it covers approximately 500 clinics and units, but it doesn't include the psychiatric clinic, of course, for obvious reasons. And this makes it about 160 million hospital events, where an event is actually either a diagnosis code, a drug prescription, or a test or anything. Of course, it's not very easy to get access to this data set, but as soon as you get access and you get ethical approval for a particular task, and in our case the task is to detect adverse drug events and also study heart failure. So as soon as you have a particular project that is funded by some valid agency, then you can apply for ethical permission and get it. Okay. So what we are looking at, so our main motivation was adverse drug events. And the main idea was we had a previous connection with AstraZeneca, and their main concern was that, okay, so many adverse drug events are not identified as such after the drug is employed because clinical tests are not good enough. So when the drug is deployed and people start using it, many new ADES could occur that have not been captured during clinical trials. And the main idea is to learn from the history of the patients, use electronic health records and machine learning to actually identify those new ADEs. So there are several lines of research here, and the main bottleneck or the most important key step is what features to extract from electronic health records so that they are informative and then you can use them for detecting ADEs. There are two approaches actually. One is to look at static features, mainly take your favorite window of interest, for example, 1 month, 2 months, 90 days, or a year, or whatever our medical experts recommend, and then extract some aggregate features from this in these windows. So these are called the static representations or static features. So mainly you choose your AD as your very nice column class label, and that AD could either be a positive or negative, yes ADE, or no AD has a binary feature actually, or it could be actually a multi-class problem. And then you pretty much aggregate the different types of features. For example, whether a particular drug has been prescribed, or how many times it has been prescribed within a period of interest, what blood tests have been taken, and so on. And then you can run your favorite algorithm. I will keep claiming that random forests are super competitive here, because of course our group is using random forests, and historically one of our former professors, Henrik Bostrom, was the person behind random forests. So I keep claiming that random forests are very, very promising for this particular problem. Now what we observed though was that if we aggregate the features, then we're losing a lot of information, and we're losing a lot of temporal information. So, for example, consider now that your data set could contain several static features, but then if you have, for example, blood tests or measurements of some particular substance in the blood, these variables can just change over time. And even the more complex thing is that the measurements are not taken at equal time intervals. Okay. So the main question is, how do you deal with those features? Okay, if you aggregate them, you might lose their development over time. Okay, there are several approaches that actually do this aggregation, but they don't work very well. And there are 3 highlights or paper highlights. So this paper has a very long title. That's why it's taking a lot of space. But this is the most recent one that we came up with in our group, and then we have two earlier ones. So the main idea, which is actually finalized here, This was done actually, this was progressive work. The main idea is to have come up with 3 phases. First phase is to take those temporal features that evolve over time and come up with a nice summarization and conversion to symbolic sequences. Okay, so instead of looking at the time at the real values, and then we come up with a subspace selection approach where you actually choose narrow down the features to the most important ones using some information gain type of feature selection, and then eventually we transform the space to a reduced representation. So let me guide you quickly through this. So the first thing we do for each column, so each column is a feature that is multivariate. What do we do first? We do a simple Z normalization. So we remove the mean and divide by the standard deviation. And then we apply a summarization technique. That's one of the simplest ones, piecewise aggregate approximation. So mainly what this does is, if the original time series or multivariate time series is of size d, meaning you have d measurements of that particular variable, you reduce it to size w by taking averages for every w measurement. Okay. So mainly this idea is mainly to reduce the number of measurements. And then the next thing we do is we do what is called an abstraction. So instead of looking at the actual measurements, meaning, okay, I can give you a simple example, it might not even make sense to say that, okay, this patient's temperature was 37.2, then it developed to 37.4, then 37.5. That's useless. The temperature was high, or not very high, but not normal. So instead of looking at the actual development that doesn't really that doesn't vary too much, we can map it to a simple symbol that covers this period. And what we used here was the Sachs representation. So the Sachs representation is mainly what it does. So suppose this is the original time series. Okay. So we decide on the number of the size of the alphabet. Let's say in this case that we want to map the time series to an alphabet, to a symbolic sequence of 3 letters, A, B, and C. So what do? We assume that these values, the time series values, are generated by a Gaussian distribution, and then we mainly, so this is the Gaussian distribution spectrum, and then we cut off the possible values into equal areas, and we assume that every value from whatever, from -infinity to this cutoff point, so whatever falls here will be given a particular letter. In this case, it will be, let's say, C. Whatever falls here, it will be a B. Whatever falls here, it will be an A, and so on. Okay. All right. So after we do that, this mapping, then the real values are reduced to a string. And then we define what we call subsequences, or S shapelets in this case. So the idea of a S shapelet is actually borrowed from time series. So for time series, a shapelet is a distinctive subsequence, is a class distinctive subsequence. Here, it's the same thing. It's a symbolic sequence that is class distinctive. Okay. So mainly, what do? We look at our converted features, and we take random subsequences of length that could be from even 1, so 1 measurement, to the maximum size or sequence size we have. So we generate those random sequences, and we evaluate them based on their utility, so their class distinctiveness. And in order to do that, so what do? So for each particular shapelet, we check its distance to every single multivariate feature. And in our case, the distance is the best match it would have to, suppose this is the Euclidean distance, so it's the best match it has to each record in the multivariate feature. Okay. So then we come up with a value. And let's say now each multivariate feature is converted to this set of values based on a selected shapelet. And by doing that for a big set of random shapelets and for different alphabet sizes, meaning for SACs, we can come up with a shapelet that has the best utility. So it has, for example, it achieves the highest information gain. And eventually, and we also, the shapelet that corresponds to that high utility has an alphabet. That alphabet size is actually the alphabet size that we're going to use for that particular attribute. Okay. And finally, we get a set of shapelets per feature. So for each feature is mapped to an alphabet size and a set of shapelets that are the most distinctive for that feature. Okay. So as soon as we have done that, we have learned actually a mapping function that takes the initial feature space, maps it to a set of real values, including a set of reference shapelets per feature and an alphabet size. So when a new example comes in, then the same conversion is performed, and and the classifier is, and your favorite classifier could be applied here. In our case, we tried several. Random forests, of course, by strange coincidence, perform very well. One interesting challenge that we had here that hasn't been addressed in previous works is that this type of data sets are super sparse. Super sparse meaning that when a patient comes to this hospital, they will never measure every possible variable that exists. Okay. The doctors find what is of interest, and then they would only measure 1, 2, 3, maybe 5 variables. And so this type of data set has extreme sparsity. So many of those features will be empty. Okay. So what do? So if we have a shapelet and we want to find the match or the distance to an empty feature, and we apply the edit distance, for example, here, then the edit distance will be equivalent to the size of the shapelet. So it won't give us too much. So a simple heuristic we do here is mainly when we compute the information gain. Okay, just to give you a simple example, let me show also here. Suppose that, okay, these are the red examples. We have two classes. These are the red examples and these are the blue examples, and Z are the examples for which that are empty. So the feature is empty. So mainly what do? We make two trials. First, we assume that those features that are empty have 0 distance from the shapelet that is of interest. So mainly they are assigned to the very left side. We check the information gain. Then we do the same thing, but assigning those features, the empty features, to have the maximum distance to the shapelet. And then we compute the information gain again. The one that gives the maximum will be the one that will be chosen. Okay. And we call this left-right encoding. It's very simple, very heuristic, but it works quite well compared to ignoring those values or taking the most frequent value. So what we have currently out of this health record, electronic health record database that I showed you, we have 19 different adverse drug events. And these are adverse drug events, these are ground truth events, so these are actually annotated by the doctors. Okay. And we assume that the doctors haven't made any mistake. So we have, these are the different ADES that we're looking at, if you want to read them. And then we have positive and negative examples, and this is the number of features. These are the number of features per ADE, per data set. So what we did, we applied our method, and we tried to see how it behaves. Okay, this is a summary table. So if you look at how AUC develops as the feature sparsity increases, you can see that AUC actually increases for the more as the number of features that are sparse are included in the dataset. So what you see here, this percentage means, so 20% means that we allow only features that are sparse by at most 20% to be in the dataset, to be included. And this is at most 30%, at most 50%, and this is the whole dataset. Okay, good. So on average, what we observed also was that shapelets or S-shapelets that were of rather small length, between 2 to 8, were preferable or preferred compared to larger shapelets, with barely any shapelet having a size more than 20. The other thing that we observed was that if we try to do the similar conversion without doing the Sachs representation, but by just simply using the doctor's annotation, mainly if the blood, if a blood measurement is abnormal or normal, then we map this to a letter, normal or abnormal, or if the temperature is high or normal. So if we do this conversion, unfortunately this gave us a worse performance than actually using the automating it through the Sachs representation, which was quite interesting. Okay. Good. So let me move now to the second part, and I guess we can discuss the first part later on if you have any questions or comments. Now the second part is more like an interesting hobby that we started having in our group about 6 or 7, well actually 1 year ago. And then it gave us a very nice paper. So the main idea was that we built a very nice classifier for multi-channel time series. And our application was electrocardiograms. This is one channel here, but suppose it has like 12 or 15 channels. And we built a very nice shapelet, random shapelet forest that actually can predict the class label of this ECG. Of course, since it's a random forest, it's a black box classifier. Well, we gave that prediction to our doctor collaborator here. This is actually a real person and a real patient. This is our cardiologist who assesses our findings every now and then. And our classifier is really good at saying that the patient will die, for example, by heart failure within 2 days with very high certainty, period. Okay. The doctor told us, okay, great, thank you very much, but this is useless to me. I'm not looking for an oracle. I'm looking for something that can actually tell me what is wrong with the patient exactly so I can fix it. So this black box classifier here is of no use. So he gave it back to us and we had to do some more homework. The idea that we came back with, it's not, of course, we're not the first ones to propose that, is we wanted to figure out a way that the classifier would actually tweak its predictions, tweak its features so that the predictions would change. Okay? So the classifier can come up and tell the doctor, well, if you change this particular parts of the time series, then my prediction will swap. Okay, and this comes from an idea that appeared by Ptolemy and others in 2017 on actionable feature tweaking for random forests particularly. So suppose you have a random forest model, which is an opaque model, and you have an example, and the random forest comes up with a prediction of -1. Let's say you have a binary classification task, +1, -1. Which means that the ensemble is predicting -1. And let's suppose that X is a true negative instance. Okay. So the goal now here is to find the minimum number of changes we need to do to the features so that the classifier will swap the prediction. Okay. So we assume that the classifier is doing the correct thing, and our example has a label, and we want to make sure that we want to ask the classifier to do the minimum number of changes to the features of X so that the prediction changes. All right, and well, this is pretty much what we are after. Okay, so we were inspired by this very nice paper and this nice idea, and then we pretty much we thought of converting it or applying it to time series. Okay. So just to guide you very briefly through this idea, so if X is a true negative instance, as I said, the goal is to find the minimum number of tweaks so that the classifier will swap. So now if we let's make a couple of observations. So if the prediction of the random forest is -1, then it means that at least half of the trees will predict -1. Okay, that's very obvious. And if the prediction of a tree is -1, then it means that at least half of the paths might predict -1. So the solution is to try to revert those paths, okay, so that the trees will change their prediction. So we focus on the trees that predict -1 and explore the positive paths and try to force the example to go through those paths. And there's and a transformation is applied by imposing the example to go through the path. And based on the Ptolemy's idea, the main transformation we're actually doing here. So if the decision condition in a particular node in the path is this, so xi is the value of the feature and theta I is the value of the condition, then we mainly set the feature to the condition minus epsilon, so that we force it to be slightly less than theta, so the condition is satisfied. And the opposite is done for this. Okay, this is a very simple and heuristic idea, which we liked quite a bit. The problem with actually, the easy thing about this setting is that, okay, you have simple features that you can actually tweak. The problem with time series is that you actually have one single example, and features could overlap. In our case, features are shapelets. Shapelets are subsequences. So in our case, this is what we want to do. So this is a very nice example taken from the UCR, from Imon Keogh's repository from the University of California, Riverside. So this is an example of a gun draw versus a finger point. Finger point is, so that's the trajectory of a hand. The blue one is the pointing a finger. The red one is gun draw. And mainly, as you can see here, what it says is that if you change the particular area of blue and convert it to yellow, then you're going to convert it to a gun draw, in the trajectory of a gun draw. So what we want to do is actually take the original time series, which is the blue one in this case, and apply the smallest set of transformations so that the classifier will change its prediction. Okay. So we propose two approaches. What we call the first one, we call it reversible tweaking, meaning that once we make some change, we can revert the change while we're examining more paths. And the second one was called the irreversible tweaking, meaning once we do a change in a time series, we cannot revert it anymore. All right. And if you're not familiar with the random shapelet forest, our classifier looks mainly like this. So it's a simple random forest where each tree is built like a simple decision tree, where the decision nodes are bound or connected to a particular feature, which is a time series subsequence, and the condition is mainly whether that particular subsequence is included in the time series, appears in the time series or not. Okay. So the test is mainly, so if this is our test example, and this is one of our shapelets, and it appears in one of those nodes, the question is, does this shapelet appear within distance less than or equal to delta in the time series? If yes, then we follow one path. If not, we follow the alternative one. All right, so our solution, so the way we approach this is mainly that we focused on trees that predicted -1, and then we tried to force to make the conversion. So for each tree, we found the positive paths, and we wanted to force each tree to take a positive decision. So, for each non-leaf node, suppose you have a condition on, or a question on a particular shapelet and a particular theta threshold. So there are two things that can occur. The shapelet could exist in the time series, and it could be, its distance could be less than or equal to theta. All right, if that's the case, and we want to revert that, meaning the node condition could demand otherwise, what we do is that we find all matching instances of that shapelet in the time series, and we increase their distance to something slightly above that particular threshold. Okay. And the opposite could occur as well, of course. So if that shapelet in the condition node does not exist in the tree, so it means that the distance of the shapelet to the time series, or the minimum distance, is more than theta, then what we do, we actually find the best match of that shapelet, and we force it to be below the distance threshold, slightly below the distance threshold. Okay. And if we do that for each path, then we force the trees to change their decision. So the main question is, how do we do that? I can show it to you in a simple picture. So mainly what we assume, let's say this is the shapelet of interest, and assume now that theta is the radius Well, maybe I can show you this part as well. So suppose that S is the shapelet that we want to transform, and then theta is the boundary condition. So you can assume that mainly what we want to do is and this S here, up there, the dark one is the actual match of the particular shapelet in the time series under question. So mainly what we want to do, if S is on the outer side of the circle, we really want to bring this shapelet actually to be slightly smaller than the radius. So we want to bring it slightly inside the radius. And if the opposite is happening, so if S was inside and we wanted to make it less than theta, we would like to bring it slightly outside. And if you do some simple linear algebra, you can actually find the coordinates of this shapelet. If you assume that each shapelet is an m-dimensional point in the m-dimensional space, and your distance function is the Euclidean distance, you can uniquely define this. Okay. All right. And of course, there are two approaches, two ideas here. One idea is that changes can override, so as the previous transformations, and the other idea is that changes cannot override. Okay. So in the irreversible time series tweaking, suppose that you're following a path now in your particular tree, and you're making one of these tweaks. In the irreversible time series tweaking, we assume that once you make a change, you cannot revert it. So once you're following a path and some part of the time series is changed, so this position is locked. And then if you follow down the path and there is another change that demands some overlap of the previous change to be reverted, this is not allowed. Okay, so this is just one way to make this faster. And then the good thing about this is that it also allows early abandoning of the transformation. So the Euclidean cost will always keep increasing. So you can, if the cumulative cost while you're computing a path is above the best match, the best successful transformation you have so far, you sort of abandon examining this path. So this is the most naive way of doing it. And then, of course, you can do the opposite, which is, I guess, the best performing one, which is the reversible time series tweaking. So changes can override previous transformations. So we start the path from top to bottom, and every time a node conditions demands that a particular subsequence should be changed, we just apply the change. And here we can do something simple to speed up this test. We observe that the bottleneck here is the prediction of to come up with the predictions of the ensemble. Reverting the paths or computing the costs of each path can be done very fast. So mainly what we do is that first we compute the cost of all the paths, we sort them from smallest to largest, and then we try each one, we compute the ensemble based on each one of them. And as soon as we reach the one that for which the class label is flipped, then that path is the one that we report, because that has the smallest cost. All right, so the experimental setup, we tried quite a few experiments here, but I'll give you a flavor. So the UCR time series repository consists of 85 different data sets. We focused on binary for simplicity, but now on the extension of the paper, we have all of them. One very naive competitor is the 1NN classifier. So for example, what do? We just look at the first nearest neighbor with the opposite class. And the evaluation metrics, they're always very hard. It's always very hard to come up with an evaluation metric when you evaluate interpretability, and we didn't want to immediately involve experts because there are many questions there that need to be addressed when you involve experts. So the first thing we looked at was the average cost, meaning how much of the Euclidean distance needs to be changed. Okay. And the compactness of the transformation, mainly what fraction of the time series needs to be changed. Okay. So what fraction do we need to change, and by how much do we need to change it? Okay. And of course, we want to minimize both. Okay. So here's some samples, some results samples. So here we have the cost. Here we have the compactness. Accuracy you can pretty much ignore. This is mainly just for reference. So this is the accuracy of the random shapelet forest versus the nearest neighbor classifier, the 1 and n. This one is the reversible, irreversible, and the nearest neighbor. So the results are not super surprising, right? So they were pretty much as expected. So reversible tweaking results in the least costly transformations, because that's how it's designed. Irreversible tweaking results in the most compact transformations. Compact meaning it changes it doesn't change much of the time series, which is of course it's designed this way because it does this locking. This is a nice. The baseline is way too naive, the 1 and n. That's why we extended it to k and n to make it a bit more attractive. And here's an example output. So in using ECGs. So this is a normal heartbeat. This is an this is an abnormal heartbeat, and this is a normal heartbeat. So the dashed line is the nearest the 1 and n transformation, whereas our the reversible time series tweaking would actually suggest only these 3 parts that need to be changed so that it's converted to the blue one. Okay. So quick conclusions. This was for this particular problem. This was a quite novel time series problem for time series interpretability, and very simple approach to quite simple measures and a baseline. And it seems that it works quite decent for our measures at least, and for a variety of data sets. And you can read more about this in this paper, plus the arXiv version. And what we're looking at currently here, we're looking at we extended this already to the k-nearest neighbor classifier, including humans as well as evaluators, but again, we don't like that so much, so we try to keep it, to avoid it, but I guess we have to do it. And we're currently also looking at other types of feature transformations, because now we're looking at only simply at the time domain and tweaking it under the Euclidean space. So for example, if we look at the frequency domain and start removing or tweaking the frequency spectrum so that the classes change, that could also be quite interesting. And of course, other application domains would be of interest. All right, so very quickly I can also summarize what else we're looking at here in these data sets, because this was just a very simple example. We're looking at clinical text mining as well. We're looking at conformal prediction. Conformal prediction meaning that if you have a set of predictions, we're not only interested in the actual class label, we're also interested in how certain or how confident the classifier is for a particular set of class labels. And we started playing with also parallel computing using GPU programming, which is quite nice. And another interesting problem is how to integrate multiple data sources from electronic health records. Mainly what we're trying to include now is chemical compound data from AstraZeneca. So we currently have been looking only at the labels of the drugs. So mainly there is something in the molecules that could also, in the molecule structure that could also hint for a drug interaction. And as I said earlier, interpretable models are quite interesting for us. And also personalized medicine, that's another interesting project that we have. And of course, I should thank my team and the co-authors in those 2 particular papers. This patient is still alive, so luckily, but though he looks very sick. And good. And finally, instead, if people are interested, not here, but we're going to be opening 10 PhD positions in total, 1 definitely on machine learning and model interpretability, and 4 open topic positions. So thank you very much.